Hi everyone. We have Matt Fontaine here today. Matt is a PhD student at the University of Southern California, advised by Stefanos Nikolaidis. Prior to coming to USC, he completed his bachelor's and master's degree at the University of Central Florida, and his research focuses on the problem of automatic scenario generation for robust human-robot interaction, as well as the algorithmic foundations of quality diversity optimization. He's published algorithms for quality diversity like covariance matrix adaptation map elites and map elites via a gradient arborescence, as well as quality diversity for generating human-robot interaction scenarios like deep surrogate-assisted generation of environments. Matt's work has been published in RSS, Gecko, and AAAI, and his work on differentiable quality diversity was recognized with an oral presentation at NeurIPS 2021. Today, he'll talk to us about quality diversity scenario generation for robust autonomy. Go ahead, Matt.
Oh, yeah. Thank you for the nice introduction, Laura. And I guess we'll get started. I think we have a lot of overlap between our two groups in terms of interests. And so without any delay, I'll dive right into the topic for today. But before we get into scenario generation, I wanted to talk a little bit about what our lab does. So back when NeurIPS was in person in 2019, we had a hairbrushing demo. So we work a lot with these physical robotic arms and robotic systems. And so this hairbrushing problem is really interesting. If you have a stroke patient that can't use their hand, we can assist them in combing their hair using a robotic arm. But this problem is really interesting because if you look at, everyone has different hair types, different hair lengths. And we need a system like this to be able to work in all different kinds of settings, and not just for one person. Another interest in our lab is robots collaborating very closely with humans. So here's an IKEA assembly task, where the robot's handing parts to the human being and kind of predicting what part they want next and assisting them as well as possible. And this is, you can see, this is a very complex interaction. It's over a long time scale. You have a human in the loop, so that's very complicated. And just everything gets really complicated with this kind of example. And so for my PhD, I started thinking a lot about well, if these systems are going to become more and more complicated and we're going to have humans in the loop, we need better ways to understand and test them, for any autonomous system than we currently do. And so that's kind of the broad research question I focused my PhD around. And one really big observation I made very early on is scenarios need good coverage. You don't want just one scenario that is maximally bad if you're testing it. So if you're looking for a failure, you don't want the worst case failure scenario that you can have. You want to make sure you cover all your bases. So for hairbrushing, I want to know, does this work on different hair lengths or different hair types? And so that's an example of good coverage that we would need in that scenario. For something like IKEA assembly, people have different preferences. So we'd want to make sure that we're testing different order of preferences in terms of putting IKEA together, because no one follows the directions and they go out of order. It seems also adaptability, a robot may hand a human a part and then the human might not be ready for that part. And then they'll change to be more like what the robot wants to do rather than what they want to do. So it needs to be able to work in both those kinds of settings. And then we've also done some work on shared autonomy, where you have a joystick and you just can nudge the end effector in a certain direction. The robot figures out what you want to pick up and helps you pick up that object. And that needs to work in really cluttered environments, but also really spread out environments. And also it needs to be able to handle different amounts of noise in the actions, because we're not all as good at using a joystick as everyone else. And so the observation I kind of made is good coverage is domain dependent. If you wanted to test one of these systems, you need to kind of set up that system for the domain, and you need to specify what good coverage means. And so we needed a way to do that. So I started looking through different classes of optimization methods to kind of line up with this scenario generation problem. And so one way is you could have single objective optimization. So if you had a function that told you how bad a scenario is, you could just maximize that function and find a single point of failure. So you want just a single extreme point. Or if you had multi-objective optimization, you may have two different ways a scenario could be bad. And then you can find what's called the Pareto front, so that you end up having these trade-offs between the two objectives and find all those points along that trade-off. And so neither of these really looks like what I was looking for. But then if you look at diversity search algorithms like novelty search, they also have functions, but those functions are functions you want to span. You don't just want the extreme point, the max or the min. You want like pretty much everything kind of output the function can have and have good representation over those functions. And so then I really started getting interested in quality diversity optimization because it just combines these two. So you have an objective you want to maximize, but you want to maximize it for every point that can come out of this other function that you want to span. And so that's really what I've like focused a large part of my scenario generation research on, is how do we frame this as a quality diversity optimization problem rather than single objective, because I feel like it lines up much more cleanly with the problem I'm trying to solve in my PhD. We can also formalize the problem, which maybe you haven't seen in talks, like a formal definition of QD. But here it is. So let's say we're optimizing some continuous space, just like single objective optimization. You have an objective that you want to maximize. And then you have these K functions we're going to call measures. And we want to span these functions. You can just treat this as a single mapping as well to a low dimensional space as a vector function. So if you map your search space down to this low dimensional space, then what you really want to find in quality diversity is a solution for each point in this thing called the measure space. You want to find a solution in search space that maps to that point. And then also out of all those points, you want to maximize the objective. And that's what a quality diversity problem is. That's like the crux of what we're solving. And if you think about like, well, what does a QD algorithm get you? It's not getting you a single solution point, it's getting you a collection. And so here, what we have here is we have two measure functions. One is boldness, so if we can measure like pen weight, and then the y-axis is like how gray is the image. We can basically just produce a collection of all different kinds of digits, where the objective here was to find something that looks like an 8, like an MNIST digit 8. So if we can formalize a problem with these functions, then we can get like basically a data set of 8s that vary in the way we care about, which is very good for testing systems. So the simplest thing we can do to solve this quality diversity problem is map-elites. So map-elites, you have a high dimensional space, you map down to the measure space, you want to get the highest performing solution in each of these regions. So we do this by tessellating everything into grid cells. We sample some initial solutions and we evaluate them, figure out where they land, what cell do they land in measure space, and like how good are they. Then we uniformly randomly select one of the solutions in the cell, perturb it with a little bit of isotropic Gaussian noise, and then it'll land in a different cell, have a different objective value, and it'll just replace something in that cell if it improves upon that cell. And so the key insight here is we can use the existing solutions that we find as stepping stones to reach more complex solutions. So it's not like greedily going towards the objective in every step, it's just moving around this low dimensional space. And the concept is that can help you find more complex solutions in other parts of the space. But one of the issues here is like map-elites is a very, very simple algorithm, but it's also very simple and efficient. And so one of the first problems I worked on in my PhD is how do I improve the sample efficiency of map-elites for continuous optimization? And so the candidate that I found that I thought I could improve the most on was these isotropic Gaussian perturbations, because the algorithm behaved more like a sampling algorithm than optimization algorithm. And so I thought, well, how can we frame QD as an optimization problem itself? Like it's solving some kind of optimization. And if we go back to the quality diversity problem definition, we actually have an objective. So we have a single objective for quality diversity. But the thing that's neat about this objective is it's defined over the archive, which is the discrete set of solutions, like the grid cells. And so we can just formulate this problem as the sum of the objective values over the grid cells. And the problem is we just want to find the best archive. So we want to find the max of this function. And the thought was, well, maybe we can just do gradient descent directly on f of QD, which is the QD, the objective of the QD problem. And this is kind of a problem because our archive is discrete. So if we want to compute the gradient, we can just take the concept of a gradient. What does it mean to be a gradient? Well, it's the smallest change that you can make that results in the steepest increase to the function. That's kind of the conceptual definition of the gradient. So what we're going to commit to is the smallest change we can make to an archive is adding a single solution. So we're just going to commit to saying we have a solution point in an archive, and we want to improve the archive as much as possible by adding the solution. Can we take the gradient with respect to this solution point? And so the gradient with respect to the solution point is just the improvement over the incumbent solution. And so then we can just take the gradient with respect to the search point now and get something like gradient descent. And what we're going to do is just approximate this gradient with CMA-ES. So CMA-ES is a natural gradient optimizer. If you haven't heard of this algorithm, it just maintains search directions as a multivariate Gaussian. They approximate the natural gradient with some uncertainty, and we just plug that in and run it as a quality diversity algorithm now. And so this is what CMA-ME looks like on a benchmark function. And you see it fills the measure space much more efficiently than map elites, and also can find higher quality solutions. We also did a little bit of agent training using this for the game Hearthstone. So we created some agents to play Hearthstone with different kinds of strategies. So we wanted to find high performing strategies for Hearthstone, but also varied in their strategic approach. So we can just represent a strategy as a neural network. Instead of representing the policy network of what actions the agent could take, we just represent it as a value function that we're going to use for a tree search. Hearthstone has a lot of complex actions. So we just have a value function that evaluates the board state. But then we can directly optimize that value function using CMA-ME based on the induced policy. Rather than learn a value function that's accurate in terms of the MDP, we just only care if it induces a policy that wins games. And so then our objective is how many games can we win? And then our measures can be things like how big was our hand on average? So are we saving our resources or burning them all at once? Or a measure could be how many turns does the game last? Do we go directly for checkmate, or do we try to extend the game as much as possible? And so with one run of this algorithm, we can basically explore the strategy space and get all different kinds of ways of playing Hearthstone. And you see map elites really struggles at extending the game, but CMA-ME is much better at extending this game over time. And then at the end, the center starts to light up because it realizes, oh, if I survive for a while, then I suddenly start winning games. So even though there's this sparse reward, I've got these nice stepping stones towards much better strategies. We also tried optimizing these policies directly with CMA-ES. And so CMA-ES, the QD score is basically the QD objective I presented earlier, the sum of the grid cells. But you'll see that CMA-ES is actually a better quality diversity algorithm early in the search. But then it starts converging to the best solution, and it gets passed by map elites, both variants of map elites that existed. But CMA-ME kind of takes off at the same slope as CMA-ES for the exploration, but it just keeps going in terms of finding all kinds of different strategies. So that's a promising sign. But we can also look at the best strategy it found at any given step of the search. And we see that CMA-ES and CMA-ME kind of stay close to each other early in the search. But then CMA-ES converges, so the map elites ends up passing it in terms of its best solutions. But then CMA-ME, we're not losing anything in terms of the best solution, even though it's trying to find diverse solutions and eventually gets even higher performing solutions than map elites. We also have an open source implementation of QD and the CMA-ME algorithm, and basically all the algorithms I'll talk about today that has a lot of tutorials and things, including this lunar lander tutorial. So I didn't change the reward function here, I just changed the measures. And you can find a way to land it like a space shuttle, because I grew up in the space shuttle era. So this is just the proper way to land spacecraft. And so you can look at documentation and tutorials if you want to use QD in your research. Okay, so now we know a little bit about QD algorithms, but then the question is, can we use this for scenario generation? And so what I want to talk about next is how do we improve the actual generation of scenarios? Because I want to have this loop where I use a QD algorithm to sample scenario parameters, generate a complex scenario, evaluate that scenario, and then collect all different kinds of scenarios that cover the space, wrapping it all in Qt. And so we can just formulate this as a research question. We want to generate complex and realistic environments. And so we had this paper at RSS in 2021 that studied this problem. And our motivation here is like, we want to deploy robots in the home. That's a big goal of us in our lab. And everyone just arranges their home differently. We have different constraints on how like tight the kitchen area is. And if a robot's going to be deployed at scale, it needs to basically work everywhere. And so we ended up coming up with some constraints for like what good environment generation means in these settings. So the first one is the environments need to be realistic. We don't really arrange our homes at random. So there's not a point in getting the robot to work on like really contrived, like upside down furniture that's stacked in some really bizarre way. We also want environments to be valid. So it should be possible to solve the task for a human robot team. It shouldn't just be that we want arbitrary environments, like if they're impossible. And lastly, we want to make sure that we get diverse coordination behaviors because we want to test the ins and outs of these autonomous agents. And it's very important that they exhibit diverse behavior. So we studied Overcooked. So here you have a human robot team. So the robots in green, the humans in blue. And they're putting some onions in a pot and cooking some soup. When the soup's ready, they plate the soup and they deliver it to a serve point. And this domain's become really popular in human AI coordination. And so that's why we decided to study this initially. And so to give a little more information about our simulated human, it's just running a planner to go to the next subtask and greedily deciding its next subtask based on some preference. And the robot is solving a POMDP where its observations are the human state in action and also the world state, but it doesn't know what the human's trying to do. And so it's like the hidden variable it's reasoning over is like, what's the next human subtask? And POMDPs are NP hard to solve, so we're just approximating it with a QMDP. And so now that we want to test these systems, we go over our environment generation framework, which is very similar to the general form I showed you. And I'll just go through it piece by piece. So the first piece is we want to generate realistic environments. We could really use any generative model here, like a VAE or a GAN that has a latent space. We want something that maps to some continuous variables to an environment. So we use the GAN. And our training data was all the Overcooked levels that existed in the actual game, since Overcooked is based off a video game. If you end up generating environments, they're realistic. They look like a real Overcooked level that you would have, but they're invalid in some way. GANs are not as good at capturing complex constraints in environments. And so what we can do is we can use MIP, like mixed integer programming, to repair this environment in a minimal way to satisfy all the constraints. So constraints are reachability. The agents need to be able to get to every key object in the scene. There has to be the correct number of stoves and kitchens. And if we satisfy all these constraints, then it'll at least be possible for an agent team to solve the task. And then we just simulate the agents and see what they do. So we can measure their coordination behavior, and that becomes our measure functions. We can measure their performance, how well did they do? And then we can find different environments with different performance and different agent behavior. And then we wrap this whole thing in a quality diversity algorithm like CMAME, searching over the latent space of the GAN, and then updating an archive of all these different environments that have different behavior. So with one run, we can get different measures of team fluency. So on the left, we have a high team fluency environment. Each player basically has their own workspace that they can work across, and they grab the soups independently. They keep moving independently, and they can survive the level. But on the right was a low team fluency environment our system found in the same run. And so you get this narrow hallway in the corner where the agent is trying to deliver some soup, and then the human has to wait for them to get out of the way so that they can deliver the soup. And so it creates this bottleneck for coordination that makes it hard to solve. We can also find edge cases. So here the robot took an onion, but then the human's going to just go and finish the job for the robot before it gets there. And the robot gets confused because it thinks that, oh, if I start a subtask, I'm going to complete a subtask. So that was like a bug in the QMDP. And then there's a second bug here where the robot can't reason over the human getting out of the way because it's only reasoning over subtasks. So this human and robot are oscillating back and forth, trying to like get out of each other's way. And the robot's kind of stupid and doesn't understand that it's trying to get out of the way rather than moving to get another onion. And so this was a really interesting edge case that we just found in the archive after running this solution. And so this can be used as a way to debugging autonomous agents. Simulated humans are one thing. We actually ran a user study online on that low team fluency and high team fluency environment I showed you in the previous slide. And we found that on real humans, if we just measure their percentage of concurrent motion, then we see that in the high team fluency environment, they're moving in parallel a lot. In the low team fluency environment, the percentage of concurrent motion goes down. And this supports our claim that like we can induce different agent behaviors just by changing the environment. And so this is an overview of that environment generation system that I presented, but it wasn't all created in one go. So the original paper that we first studied, environment generation was on GANs, was this AAAI paper where we trained content to generate Mario levels, basically. And then we ran CMAME and a bunch of other QD algorithms on it to generate these heat maps that have different levels. So here we have like a really large number of enemies that Mario has to jump over. So we just have an environment with lots of enemies. We also can have fewer enemies, but no sky tiles. So it's a very flat level with lots of enemies. We can have a lot of sky tiles, which was another part of the training data. And then you can have a mix where there's a lot of enemies in the beginning, but then it ends up with a lot of sky tiles at the end. The MIP repair was also done in another paper that was presented at AID in 2020. And one thing I want to point out is it scales, like MIPS, modern MIPS scale to these really large environments like Pac-Man. So here, Pac-Man has to reach all the power pellets for the level to be valid. And we can solve that reachability problem really quickly with a MIP, and then have the min cost edit distance between whatever the GAN generates and something that's valid. You also can't have dead ends, like we have a dead end over here, and the left and right side don't match. So we can make a minimum edit to this level and still get it to be completely valid Pac-Man level to guarantee playability constraints on what comes out of the GAN. The even like cooler thing about this paper is you can do this training end to end where the MIP is actually in the training pipeline, because you can send gradients backwards through a MIP using this AAAI paper from the same year. And that's what we did for the GAN training. And it actually helps the GAN converge faster, which is really exciting. Okay, so now we'll move back to our scenario generation framework. And we talked a lot about like, how do we generate more complex scenarios? Now what I want to do is I want to move to scenario evaluation. And the reason I want to move to a scenario evaluation is really my goal is to be deploying these on these really complex, like this IKEA assembly example, where this is a really complex scenario being like over a very long time scale that takes a long time to simulate. So simulating the robotic arm, simulating the furniture pieces, that's going to take a long time. So we really need to improve the rate at which we evaluate scenarios. And that really motivated this paper that was accepted to NeurIPS yesterday that we're really excited about, which is deep surrogate assisted generation of environments. So the idea is we want to replace scenario evaluation with a surrogate model of scenario evaluation, and then use that to basically speed up the same QD environment generation pipeline. And our inspiration for this idea really came from Adam Geyer's work. He did some great work on Gaussian processes and surrogate models. So if you had a Gaussian process that can model a search space surrogate model, you can speed up map elites using that idea. And he had an algorithm called ACCEL that did that. But then we started thinking, well, maybe we can just use like neural nets as surrogate models and use them to predict both the objective and measure functions of our QD optimization problem with a neural net. And then it'll speed up environment generation. And so really the key observation, or like why we thought this might work, is if we look on the left, like map elites, we call it a QD optimizer, but it's really a data generator. Like it's really in the data set generation business. But the problem is you need a lot of evaluations to get a good archive that gets like all the kinds of solutions that you need. And a deep neural net's like really fast for prediction. You just have a forward pass in a neural net. That's a lot faster than evaluating robotic arm, but you need diverse and high quality data to train a neural net. And if you don't have the data, you can't use neural nets. And the key insight is like one can help the other. And that's really what this paper is all about. So if we exploit a deep neural net with QD, then we basically have more diverse and better content that we can end up training on and get a better neural network. And as the neural net gets better because it has better labeled training data, then the QD algorithm will start finding better and more high quality and diverse content, basically. And so the first step, if you wanted to approach like this, is if we had some neural net so we have our pipeline from before, we have a generative model that goes from some latent vector to a Mario level, let's say. And then we have a neural net that takes the Mario level and predicts what the agent will do on this Mario level. Then we can basically just run this for like a couple million iterations and get an archive of, it's not necessarily diverse Mario levels, but they're diverse in terms of the predictions of the surrogate model. So at least they'll be different. And then what we can do is we can downsample that archive. So we have a little bit less training data. So we get more outer loop iterations. And we can use those same latent codes to generate Mario levels and then simulate Mario on them and figure out like how well does this agent do on this Mario level? How does it perform behavior-wise? And then if we take all of that labeled training data now, we can update a data set of training data to use to train our surrogate model and get better and better surrogate models. But you'll notice this data can also be used to form a new archive on the outside of this loop where it has all the ground truth data as opposed to the predicted data. And so then we send this neural net backwards to the inner loop, and then we end up using it to get better training data based on the predictions of the surrogate model. So we basically try to find data that the surrogate model thinks is good. If the data is not actually good for the surrogate model, then we label it and it can correct its own errors. So it's really exciting way of like generating environments. Another issue is like unlike reinforcement learning where you have access to like the MDP interaction, the environment's not really taking actions against the agent, but it is operating in an MDP. So we decided, well, let's use all that data that the agent is producing because the agent's producing a trajectory as it moves through the level. Can we just predict the occupancy grid of like where the agent was in the level? So here's all the predicted positions that the agent could be. And if we use all of that self-supervised data, we can form a much better surrogate model where we just stack that occupancy grid with the level and predict the performance of the agent. And this really helps in the paper. So we have lots of ablations on this. We also started getting really curious with your guys' group and ACCEL and just kind of all this like open-endedness work for getting these really robust agents. And we thought that it would be interesting to try using DSage against one of those agents. So we're thankful that like Jack sent us the ACCEL agent to train on. This is also an A-star agent that's still state-of-the-art on Mario. So if you have PCG in the mix for Mario, like RL still doesn't win. This A-star agent still wins. And so we're basically just going to evaluate these two things on these two separate domains. So here's an example of ACCEL finding a solution to the environment. And what we did for one of the measures was we said, what's the percentage of the reachable environment it sees? And you'll notice that the agent actually goes and explores everything. So we can make this a measure and say like, our objective is find something ACCEL can solve, but then also find something that ACCEL can solve with like different amounts of exploration. So figure out like what kind of environments it does really good on exploration, where it does really bad. And we can use this to kind of like understand ACCEL a little bit more in terms of what it can do. We also have this example where we can find bugs. So one way we can find bugs is say like, what's the number of repeated cells? And so if we end up finding an environment that has like a high number of repeated cells, you can see ACCEL get stuck in this infinite loop. And so it is possible to have these kind of like infinite loop bugs in an agent like ACCEL, but then we can use DSage to find these kind of really weird behaviors in the agent. And so I have like another example of an infinite loop that I find is kind of interesting. So it just gets stuck in this infinite loop going around and around. And so you could use like DSage as I was thinking as a replacement for the test set, because so we have like a training set for these open-ended general agents, and then we can replace the test set with something like dsage that does it adversarially to the system. We can also, what's interesting is A* agent is like as planning agent, so we can use it to test agent with like different kinds of behavior. Doesn't have to be an RL agent. And you can see there's kind of this bug even in like an A* agent where like the A* agent's pretty smart, it's doing a lot of complicated things, but it can get stuck in an infinite loop as well. And so even though this is using planning and has access to the game's forward model, like we basically can still have similar bugs and dsage can automatically find it just by seeing the behavior of the agent. Okay, so we've talked about like the framework going around the loop so far with scenario generation, also speeding up evaluation. The last thing I want to talk about is just, I want to return to the QD algorithm portion and see if we can do even better. Because we've changed a lot on like how we're generating environments. So I think we can do a lot better in QD space. And the main observation we made for this was we're really treating F and M like black box functions. So we're saying that we don't have derivative information at all on these functions. And like QD up to this point has been a black box optimization problem where we approximate gradients or do something like that. And I was really inspired by a lot of the work in the generative art community once OpenAI's Clip came out. They started creating these pipelines that was like StyleGAN, you generate an image, you have Clip, and then you specify some text and you get some loss for the objective with respect to, you can calculate the gradient of the objective with respect to a latent space, and then optimize a latent space to find the best objective. And I was like, this seems a lot like the pipeline I've been building for like scenario generation up to this point. And so the big change here is now this is a differentiable pipeline. I can take advantage of the fact that I have gradients on this function. And I thought, well, maybe we can do something with quality diversity optimization that's very similar and say that just change one word in the problem definition that F and M are differentiable functions. And so then the question we ask ourselves is like, okay, what does a quality diversity algorithm look like now if we have gradient information on F and M? And so it's fairly obvious how the gradients help on F. So if you have an objective, like gradient descent works, but it's not as obvious, I think, to figure out how they work on the measure functions. So if we just think a little bit about like how the gradients work for F and M, we basically get the steepest change in M1 and M2 with respect to parameter space. And if we take the negative gradient, we can go in the opposite direction. So we can steepest decrease in M1 and M2 in the opposite direction. And we can kind of use these two gradients as like a coordinate system for moving around the measure space, just by picking coefficients on the gradients out here. Another thing we need to change is we have like these gradient ascent algorithms that work really well, but they're essentially like a greedy incremental search that are linear. So they take just greedy ascending steps every step towards the local optima. And we want something that behaves a little bit more like tree search, but it still has that directedness aspect, because remember, we want to maximize the objective. So we didn't want to call it a tree search. So we borrowed this term arborescence. So if you're familiar with the directed minimum spanning tree, this is the paper, the shortest arborescence problem. And so we just borrowed that term and said we're a gradient arborescence algorithm. And so our strategy for forming DQD algorithms is going to be, let's just take the QD algorithms that are derivative free and get a DQD counterpart. So let's start with Mapleats. Mapleats, its primary operator is just introduce Gaussian noise on the parameter space and then see where it lands in the search. And so all we're going to do is, instead of doing Gaussian noise in parameter space, we're just going to move it to objective and measure space. So just move it from the search space to the low dimensional space. And so we're just going to put coefficients in front of our gradients now. If we sample coefficients on how much to use the objective, how much to use the measure functions, and what direction, then we can just take a linear combination of the gradients, and then we get a perturbation operator on the parameter space. And then because it's Mapleats, we just sample that from a Gaussian, and much lower dimensional space should work better. And so we actually see, although this one's not playing, but maybe if I go back, we can see that OMG Mega doesn't actually fill the entire measure space in this benchmark example, but it does do pretty well. You can't see it doing well because the video is not playing. And then we thought, okay, can we do even better? So we know map weights is like the simplest thing we can do for equality diversity optimization. Can we do something similar to CMA&E that was working pretty well on the other problem? And so in CMA&E, we have this natural gradient approximation with our covariance matrix in search space. And that's an n-squared covariance matrix on the parameters, so it's really slow. And then we can just like move this to objective measure space, just like we did with OMG Mega. And now we get something that's like k squared in the number of measure functions, which are usually low dimensional. And so we're going to do something very similar to our OMG Mega operator here, where we're sampling like coefficients that go in front of the objective and measures. And we're just going to have a similar operator where we have complete control over what direction we move in objective measure space and map that back to parameter space. But we're going to solve for the optimal coefficients that we need with CMA-ES. That's the main trick here. So we're basically solving for what's the optimal direction to move in objective measure space for our current search point. And so our insight is we could do this at the same time we branch to fill the archive, like the arborescence branching. So we branch to sample coefficients from a distribution. We use this to approximate the gradient of f of QD, just like CMA&E, except this time with respect to the coefficients rather than the parameters, and use that to fill the archive at the same time. So you get this like branching effect out in the search. So here's an overview of the CMA Mega algorithm that I'll go about piece by piece. And this was our NeurIPS oral from last year, was this paper. So the first step is we have a covariance matrix that we sample coefficients from. And then for each of these sampled coefficients, we branch in using the objective measure space to get a bunch of different solutions in parameter space. We evaluate them and see how they change the archive. And then we move to maximize the QD objective in parameter space as well, using some log likelihood estimates. And then finally, we adapt at the same time our coefficient distribution based on the natural gradient to move the coefficient distribution in a direction that we think we should be moving in coefficient space. And so if we run CMA Mega, we see it like fills the archive much more efficiently. This is a benchmark problem on a high dimensional search space. And we see that it covers the archive much more efficiently than CMA&E, MapWeights, or MapWeights line. So a very big improvement on the state of the art in QD if we have access to these gradients. But then we tried it on a real problem, which was the StyleGAN plus clip pipeline. So we can take the gradient of the objective, and that's pretty easy to do. But if we want the gradients of the measures, we can do the same thing. So we can say a small child, and that gives us kind of like a proxy for age. And we can get a gradient on the measures. So here, as you go from top to bottom, the person gets younger and younger. As you go from right to left, the person gets longer and blonder hair. And the objective text prompt, so just by changing these text prompts, you can get different objectives and measures. We end up getting this collage of Beyonce examples. So I said, give me a photo of Beyonce. Of course, you could look at this and be like, okay, this doesn't look like a photo of Beyonce, but we also use StyleGAN 1. And the second thing is we didn't use all the tricks from generative artists. They had a lot of ways to improve gradient descent on this pipeline that I didn't know about, and I learned from like Rivers Has Wings and people like this. And so we actually went back and we took all of their enhancements. We have this like dipole trick. So you can do age with like a small child and an elderly person. You get the dipoles and you can approximate a spectrum. It's a much better measure function. And so the objective here was Tom Cruise. I don't know. I think it looks like Tom Cruise now with like StyleGAN 2. So we've like, this is one of the rare examples where it's a generative model paper. You'll get much better results than the paper, like the paper results, just by using improvements from the community that are really cool. Here we have also Jennifer Lopez example. I also wanted to say that these examples weren't just generated with CMA Mega. We actually improved CMA Mega with this technique called map annealing. So this is a paper I'm not going to talk about, but it's out on arXiv. You can go read it. And it has all the tricks that I use to improve these images. So it's got a lot of formal guarantees that make this algorithm like much, much better. And so I'm really excited about this paper, but there's not enough time to talk about it. And so kind of just to tie everything together in the talk, we talked about QD algorithms, so MapWeights, CMA&E, the DQD algorithms that we can use to search spaces. We talked about scenario generators, how we can use generative models to learn scenarios from data and then search over them, how we can guarantee formal constraints on the scenarios we generate. We talked about surrogate models and how we can use them with algorithms like DSAGE to speed up the evaluation of scenarios. And lastly, we didn't talk about CMA May much, but it really changes the way the archive works in QD optimization and has some nice formal guarantees. So a paper I highly recommend reading. And so with that, I'll start taking some questions from the group.